persist? Well, of course, it's part of the energy transition, and the idea which bears repeating is to replace main engine power with power that is extracted from the wind. And yeah, so the idea in this work was to assess the performance gains for a set of appendage geometries, where in particular I'm interested in the bilge keel geometry. It's a relatively simple and I dare say inexpensive opportunity to improve the sail carrying ability of a ship. So before beginning, I think it's important or useful to agree on some variables to compare the performance. And I started with how do you say, the equivalent propulsive power, which is defined as in the EEDI. But I include also this change in resistance due to sailing. And that's, well, as you see here in these polar diagrams, that's quite a significant impact. If you look at the upwind angle, for example, changes by some nearly 10 degrees. And the magnitude of this power is somewhat, say, depressed over the range of sailing conditions. Next to this, I think it's, I would suggest that it's useful to scale this power using the available wind power over the deck. And that is to allow for comparison across a range of wind speeds. But I'll come back to that a little bit later. Yeah, so to introduce the problem, for this well-known Monk moment effect and general destabilizing moment which arises when such a low aspect appendage goes with leeway angle. You can see here in the figure, there's this distribution of lateral force shown. And you can observe in particular at the after shoulder. I don't know if my mouse shows, but in this region, there is a distinct underpressure. And you can see this also in the wave elevation at this location. And this will tend to, yeah, if you think of the ship, it ought to be turning. So it wants to finish its turn. And in order to keep a straight course, some corrective action by the rudder is required. So yeah, this situation is shown in the upper right, where the lateral force or the side force is combined with quite substantial moments. And it's easy to appreciate its origin if you look at the, yeah, this distribution of lateral force. So looking in more detail at, say, the hydromechanic effects, loosely categorized as a tip effects, if you think of ordinary airfoil theory. On the left figure, it's a CFD solution, and you can see quite nicely the introduction of vorticity at the bow and along the leading edge, or say the leading bilge, excuse me. And you can observe the same effect in the photographs on the right, which is an old wind tunnel experiment in which a thin layer of oil is put over the ship, and then you can interpret by checking where the oil is moved to find where these separation locations are and how these phenomena are. So there is along the leading bilge a similar effect. And then I would draw your attention in particular to the trailing bilge. So that's along this line here, and also over here, that there is another separation occurring there. And that's, yeah, so from the previous slide, there was this underpressure associated with the Monk moment. And the idea is to promote the flow separation at this location and hopefully reduce the magnitude of this moment. So just as with roll damping, we like to incite vortex separation at lower angles, so lower leeway angles in this case. So with that in mind, the geometries that I selected for this short desk study look approximately like this. You have at the midship, and then two farther aft, where the bilge keel 2L is twice as long as the other two. Taking a look at the, say, experimental data, I can see here the behavior for the say, the yaw moment for a few of these geometries. And it's quite clear to see that this moment is reducing as the bilge keel moves aft. And then, well, the 2L case is not shown in the figure, but if you check these hydro coefficients, you can observe that this trend continues. By the way, for the sake of the study, I did not do any attempt to scale these results. I used them simply as they came out of the experiment. And then also, I should say that this data is available online for those who are interested to continue working with it. So for the sake of this study, I developed a sort of a medium-sized chip with 4 large suction wing type devices. So that's with boundary layer aspiration to delay separation along the low pressure side. Quite a large installation, so 360 square meters. And then arranged, as you see, in this 2x2 way, which is convenient for defining a center of effort for the sail plan. As you see here, it's simply the ratio of the aft and the foresails. And this parameter is, for one, representing the range of possible center of effort locations. And then if you look at it in another way, it represents also the depowering possibilities. If you look at the definition, if the center of effort is located at 1, then the aft systems are off, so it represents a 50% power loss. So this variable is shown here in the graph. And the behavior is, as you see, for increasing wind speeds. One thing to observe is, of course, this is the true wind angle, whereas the ship is sailing with 14 knots. So in fact, the apparent wind, in terms of the, say, sailing condition, that the ship is, for all the cases here, sailing upwind. So starting from approximately 130 degrees. And it's interesting to see that it approaches a steady solution. So in the upwind case, you see here that for 15 meters per second, this centroid moves to approximately 0.8. So that's a 40% power loss. So how is this to be used in a practical way? Well, the underwater ship also has a centroid. That's the center of lateral resistance, or the quotient of the moment and the side force. And you can see the location here, and then the center of effort of the sails is somewhere between -1 and 1. And of course, the difference has to be made up by the rudder, which is conspicuously absent here, but I've deliberately left it outside of this study. So we look only at the center of effort of the sail plan, and later on also at the PWASP. So looking in detail at the upwind performance. So this is for a true wind angle of 40 degrees. These are the 4, say, variations, the reference line in gray, and then the 3 bilge keel variants. And it's, well, yeah, nice to see that, in fact, this the ship is able to carry sails with a center further aft. And yeah, as I discussed before, this is more or less correlated with a reduction in power loss. For this geometry in particular, with 2L, which in the end was the, say, best performing one, you can observe that for increasing wind speed, this centroid is moving forward along the ship. Okay, so to continue, I think it's good to spend another moment on the data reduction. Of course, on the right side, I show the combination with the wind scatter, as you're all familiar with, I think. But in this case, it's not so interesting to me to think on route-specific performance, but rather looking at the circular random case. So that's as if the ship was sailing in a circle. And then you can look at the performance per wind speed. So it's simply an average, if you will. And then finally, as I mentioned before, to look at the performance across a range of wind speeds, it's convenient to scale according to this variable. It's quite a strong correlation or dependency, excuse me. And yeah, to define such a thing, you must have a reference area, and I've simply used the projected area of the sail plan, but I think there can be other choices there. So this is P wind that represents the available wind power at the location of the ship. So just to look at how this variable moves, see here for the reference case and then for the three appendage variations, that there, yeah, if you look at it in terms of an absolute gain, it's on the order of 10%. And if it's in a relative sense, then it's really on the order of 50% in some cases. So let's say, yeah, the efficiency of the WASP installation is dramatically increased. I'm afraid I went much too fast. Yeah. Well, so yeah, so the absolute gains are on the order of 10% and approximately 50% in relative terms. If you look at this result in terms of this center of effort, which is again approximately a power loss, then yeah, the improvement is approximately by half. And then in terms of the ship's ability to harvest the wind energy, yeah, it depends a lot on this choice of a reference area, but as you see in the figure, this blue box is what I've taken. And then yeah, again, there's a considerable improvement. Looking at the results again in a graphical sense, I think would make one more comment about the true wind speed as versus the apparent wind speed. So in our case, the ship was moving, I think, 7.2 meters per second. And in fact, can observe that the slope of this curve tends to change around this location. And yeah, so the ship, in effect, when you look at the data this way, receives a boost so long as the ship speed is greater than the wind speed. That's this effect of the apparent wind. And yeah, so to conclude, I would recall this figure that is, of course, the conversion of wind energy into driving force. I always thought it was a pity there was no efficiency figure here. And of course, when you define an efficiency, you can look for improvements. And yeah, that's what we're busy with at Blue Wasp. And with that, I'll cede the floor. Thank you very much.